Okay, this time we're going to use the same problem with same data. Only one difference. This time population variance are unknown, same thing, but assumed not equal. The previously we did the same problem with the assumption of equal variances. This case the assumption is not equal variances. So we're going to use the same data for fruit punch and lemonade. That means our average and standard deviation is not going to change. So we are not going to change anything on the green part. But the critical value for t-test and the t-test statistic will change according to this new formulas. So in order to find the degree of freedom, we're going to use this formula. Let's start to see how the formula designed. First we need to find sample 1 variance. Sample 1 variance is standard deviation square, which is B9 square, and sample 2 variance is B13 square. Then we need to divide this by N1 divided by sample size. So B16 divided by B17. So I find this part. And then for the sample 2, B17 divided by B11. B17 is this divided by sample size, B11. So in order to find the numerator, I need to add up this and this, which is B18 plus B19, and then take the square of this. So I'm done with numerator. So I need to find the denominator as well. So for the denominator, S1 square divided by N1, so which is B18 square divided by sample size minus 1, sample size minus 1, B7 minus 1, and we do the same thing for sample 2, B19 square divided by sample size B11 minus 1. And then once we divide the numerator by denominator, we find degree of freedom. And we use the degree of freedom to find out the critical value right here. So I want to bring up here the function argument for this critical value. So we use t.inv.2t, probability is B5, which is 3%, and degree of freedom B22 right here. So the critical value then 2.3681. So I'm going to bring this as a graphic here so we can see on the graphic. This is two-tail because we are comparing if there is a difference between these two sample or these two population, fruit punch and lemonade. So any number between minus 2.368 and plus 2.368 would be H0, except anything beyond these points greater than 2.368 or less than minus 2.368 will be H0 reject, H1 accept. So the next step, I need to find the t value based on this formula. Let me put the formula a little bigger. So mu1 minus mu2, don't worry about this. This is always, most of the time, if it doesn't say on the problem, it is 0. So let's see this formula here. B24 is the difference between two samples, which is B8 minus B12. So B8 sample mean 1, B12 sample mean 2, so the difference is 7.78, which is on B24. So B24 minus B4, which is B4 already 0, divided by B23. B23 is the denominator of this equation, which is S1 square divided by N1, S2 square divided by N2. So because we already find this sample variance divided by sample size, which is B18 and B19, and then we'll take this square root of B18 and B19 and then divided this number B23, which is denominator of this equation, and then we come up with the test value 0.7150. As you can see, 0.7150 falls somewhere here in the H0 area. So the result for this test is the same the result for the previous test, which is assumed equal variance or assumed not equal variance. The result doesn't change, H0, except there is no difference between fruit punch and lemonade with 97% confidence level.